Long before dinosaurs, before forests, before even the idea of familiar animals, Earth hosted a world so strange it would be unrecognizable today. There were no birds, no fish in the modern sense, no reptiles, and no mammals. The oceans held nearly all life, and yet even the word animal would not fully apply to many of the beings living within them. Bodies had no established blueprint. Evolution had not yet settled on what worked best. It was still experimenting. This period is known as the Cambrian explosion, around 541 million years ago. The name sounds violent, but it does not describe a disaster. It describes an event in which life diversified with astonishing speed. Within a geologically brief moment, the planet went from mostly simple organisms to an entire gallery of complex creatures. Not refined ones, not efficient ones, just possibilities. The seafloor was a soft, dim plain of mud, interrupted by strange stalks and soft colonial organisms that filtered nutrients from the water. Movement itself was still a new idea. Many early creatures had no true eyes, no jaws, and no bones. Yet some had already begun developing tools that would shape the future of life: vision, grasping limbs, and predation. Among the earliest of these experiments was a creature so confusing that for decades scientists reconstructed it backwards. Hallucigenia. Its fossils were first discovered in the Burgess Shale of Canada, a deposit that preserved delicate animals with remarkable detail. When paleontologists assembled the fossil fragments, they saw a thin, worm-like body balanced atop a row of stiff spikes. Above it, tentacle-like limbs dangled into the water. The spikes looked like legs, and the soft appendages appeared to be feeding structures. The animal seemed to walk on stilts while dragging its limbs overhead. It made no sense, but nothing else resembled it, so the reconstruction remained. For years, Hallucigenia became an icon of prehistoric absurdity, a symbol that early life was almost nonsensical. But eventually, better fossils were discovered. Under magnification, tiny claws appeared at the ends of the supposed tentacles. The spikes showed no joints. They were not legs. The entire animal had been flipped upside down. Hallucigenia did not walk on spikes. It walked on soft legs beneath its body, and the spikes were defensive armor on its back. Its head, once thought missing, was located at the opposite end. It even possessed a ring of simple teeth lining a circular mouth. What had seemed impossible suddenly became logical, yet still strange. It resembled a distant ancestor of modern velvet worms, creatures that today live in damp forests and hunt insects using glue-like secretions. But Hallucigenia was more primitive. Its limbs were not coordinated like modern arthropods, and its nervous system was likely simple. It existed at a stage where evolution was testing the concept of limbs themselves. Nearby, in the same ancient waters, lived another organism, that challenged every expectation of anatomy. Opabinia. At first glance, it appeared to be a shrimp. Then its head revealed 5 stalked eyes arranged across its front like a crown. Extending forward was a flexible tube ending in a claw-like grasping structure. Its mouth faced backward beneath the head rather than forward. A series of lateral flaps lined its sides, allowing it to swim with a rippling motion similar to modern cuttlefish. When researchers presented the first reconstruction in the 1970s, the audience reportedly laughed. It looked assembled from unrelated parts. Eyes from one animal, limbs from another, feeding organs from a third. But fossils confirmed it repeatedly. Opabinia was not a mistake. Its design reveals something critical about early evolution. There was no fixed template for a head. Modern animals almost always concentrate sensory organs into a defined skull region. Opabinia had no such constraint. Vision spread across multiple stalks. Feeding structures extended independently. Even its orientation while feeding required flexibility because its mouth was not positioned in front. It likely used its grasping trunk to collect small organisms from the seafloor and pass them underneath into its mouth. Its swimming flaps allowed hovering, making it one of the earliest animals capable of controlled movement in the water column. But as unusual as Hallucigenia and Opabinia were, they were not the rulers of that world. The apex predator had arrived, Anomalocaris. Its name means abnormal shrimp, though it was neither shrimp nor abnormal for its time. It was simply new. Measuring up to 1 meter long, it dwarfed most other Cambrian animals. Its body was streamlined, with lateral swimming lobes and a broad tail fan that allowed agile movement. At the front extended 2 large, grasping appendages lined with spines, capable of seizing prey. Its mouth formed a circular ring of hardened plates, rotating to crush soft-bodied organisms. For years, scientists believed it could crack trilobite shells, though modern research suggests it likely specialized in softer prey. Regardless, it was one of the first complex active hunters in Earth's history. Most life before this point fed passively, filtering nutrients or consuming organic material from sediment. Anomalocaris hunted. Eyes mounted on stalks gave it advanced vision. Its swimming ability allowed pursuit rather than waiting. The Cambrian seas now contained fear. For the first time, other organisms evolved defenses not just against environment, but against intention. Spikes, armor, burrowing behavior, and improved sensory awareness began appearing in response. Predation created escalation. Evolution became an arms race. And with that race came extinction. Many experimental designs vanished because they could not compete. The Cambrian period was not only creative, it was selective. Strange forms flourished briefly and then disappeared, leaving only a few successful body plans to dominate the future. Yet, these creatures were not failures, they were prototypes. Every complex animal alive today traces its ancestry to survivors of this chaotic era. The segmentation of arthropods, the centralized nervous systems, the development of eyes, and coordinated locomotion all stabilized during this time. The world we know is built on the refinement of what began here. But at this moment in history, the outcome was uncertain. The oceans were filled with beings that looked assembled rather than evolved. Some crawled on too many legs, some swam with flaps instead of fins, some carried mouths in unexpected places. Nature had not chosen its standards yet. It was trying everything. The Cambrian world did not resemble a balanced ecosystem. It resembled a laboratory. There were no long-established food chains and no stable hierarchies of predator and prey. Each generation introduced a new design, and survival depended less on perfection and more on whether a creature's particular experiment lasted long enough to reproduce. Some species existed only briefly in geological terms, appearing and vanishing within a few million years. Others formed lineages that would eventually lead to recognizable animals. But during this era, recognition would have been impossible. The seafloor was crowded. Soft sediment preserved trails where organisms crawled, burrowed, and fed. Many of them lacked rigid skeletons. Instead, they relied on hydrostatic pressure, flexible tissues, or thin outer coverings. Because of this, most Cambrian animals rarely fossilized. The Burgess Shale and similar deposits captured an exceptional moment when underwater landslides buried entire communities instantly in fine sediment, sealing delicate bodies before decay. These rare fossils revealed a fact that reshaped biology. Modern ecosystems are conservative. Cambrian ecosystems were reckless. One creature, Wiwaxia, looked almost armored, yet not fully protected. Its oval body was covered in overlapping scales and long defensive spines protruding upward. It crawled slowly along the seafloor using a muscular underside similar to a slug. Its mouth contained rows of scraping teeth, allowing it to feed on microbial mats coating rocks and sediment. Wiwaxia seemed halfway between a mollusk and an annelid worm. For decades, scientists debated its classification because it fit perfectly into neither group. Today, it is often interpreted as related to early mollusks, possibly near the ancestry of chitons, but its exact placement remains uncertain. Its importance lies not in its category, but in what it demonstrates. Evolution was still defining categories themselves. Nearby lived creatures resembling shrimp, but lacking jointed legs as we know them. Others possessed segmentation, but no hardened exoskeleton. Some swam, yet had no fins. Structures appeared in isolation before being integrated into complete systems. Even trilobites, often seen as the stable representatives of the Cambrian, were part of this experimentation. They possessed compound eyes, segmented bodies, and articulated limbs. Compared to Opabinia, they appear normal, yet they were among the first animals to develop complex vision, capable of detecting motion and light direction. Their success came from refinement rather than novelty. While stranger organisms vanished, trilobites persisted for hundreds of millions of years. The environment itself contributed to this explosion of possibilities. Oxygen levels in the oceans had risen significantly compared to earlier eras. Oxygen allows energy-intensive tissues to function, especially muscles and nervous systems. More oxygen meant animals could move faster, sense more, and interact more dynamically. The moment movement became effective, passivity became dangerous. Burrowing began as an escape from predators. Sediment layers that were once undisturbed became churned by activity. This changed ocean chemistry, distributing nutrients differently and altering habitats. Creatures that relied on stable microbial surfaces declined, replaced by mobile grazers and hunters. The ecosystem transformed not gradually, but structurally. Among the most revealing fossils are simple trackways. Lines pressed into ancient mud show an animal moving in sudden curves or accelerating abruptly. These marks represent behavioral change. For the first time, animals reacted to other animals in real time. A trail that suddenly stops beside a disturbance suggests predation. Behavior, not just anatomy, entered the evolutionary equation. Eyes became increasingly important. Early light-sensing spots evolved into lenses capable of forming images. Anomalocaris possessed large compound eyes with thousands of facets, granting it detection of movement at distance. Prey species developed protective shells or the ability to roll into defensive shapes. Interaction shaped form. Yet the majority of Cambrian creatures would leave no descendants recognizable today. Their designs solved immediate challenges but lacked long-term adaptability. Some had too many specialized features. Others were efficient only within narrow environmental conditions. When climates shifted or competition intensified, they disappeared. Hallucigenia's lineage survived because its basic structure proved versatile. Flexible limbs, simple sensory organs, and defensive spines allowed adaptation into modern velvet worms. Trilobites survived through structural efficiency, but Opabinia's body plan, with its unusual feeding orientation and multiple eyes, left no direct continuation. Extinction during this period was not a catastrophe, it was filtration. The evolutionary process reduced hundreds of experimental body plans into a limited set of stable architectures: bilateral symmetry, centralized sensory organs, jointed limbs, and forward-facing mouths. These became the foundation for nearly all later animals. By the end of the Cambrian, the world had changed from an alien experiment to a recognizable biosphere. Predators existed in defined roles. Prey developed defenses. Sediments hosted burrowing organisms similar in concept to modern worms and clams. The chaos stabilized. Yet, stabilization did not erase strangeness entirely. Instead, it confined it. Later eras would still produce bizarre creatures, but they would build upon the framework established here rather than inventing entirely new anatomical logic. The Cambrian period represents the only time in Earth's history when complex life explored unrestricted possibility. Later evolution modified, enlarged, or specialized structures. Cambrian evolution invented them. What seems unreal to modern observers is not that these animals existed, but that they existed before rules. Their bodies were not deviations from a standard form, they predated the standard entirely. In a sense, the familiar animal kingdom is not the starting point of life's story. It is the surviving subset of a much larger imagination that nature once possessed. After the Cambrian period ended, evolution became more disciplined. The wild experimentation of completely unfamiliar body plans slowed, but it did not disappear. Instead of inventing entirely new anatomical logic, nature began distorting the existing one. Creatures now followed recognizable rules, yet some followed them in ways that feel deeply wrong to human perception. These were not soft-bodied anomalies like Hallucigenia. They possessed bones, cartilage, jaws, and muscles arranged in coherent systems. Yet a single feature would break expectations so dramatically that the entire animal appeared unreal. One of the most famous examples lived in the ancient oceans of the Permian period over 270 million years ago, Helicoprion. For decades, scientists argued over whether it even existed in the form we imagine today. The only fossils discovered were spiral coils of teeth resembling tightly wound circular saw blades. No skull, no fins, no vertebrae, only the tooth hole. The structure looked manufactured rather than biological. Some researchers proposed it sat on the creature's back like a defensive spine. Others suggested it functioned as a rolling, crushing organ embedded in the throat. Because sharks are made mostly of cartilage, they fossilize poorly. The mystery persisted for more than a century. Each new interpretation attempted to attach the spiral somewhere plausible on a shark-like body, but none explained how the teeth would grow without interfering with feeding. Modern scanning technology finally resolved the puzzle. Using CT imaging on exceptionally preserved fossils, paleontologists discovered the tooth spiral was embedded inside the lower jaw. The teeth formed a continuous conveyor belt. As new teeth grew at the back, older teeth rotated forward in a circular motion, never falling out as in modern sharks. The animal did not bite like a shark, it sliced. When Helicoprion closed its jaws, the spiral forced prey inward while simultaneously cutting it apart. The motion functioned like a rotating saw, pulling material toward its center. This allowed it to feed efficiently on soft-bodied cephalopods, which were abundant in its time. Instead of crushing shells, it specialized in gripping and processing slippery prey that would escape ordinary jaws. Its body probably resembled a streamlined shark with a long snout and large eyes, but the jaw mechanism was unlike anything alive today. The closest comparison is industrial machinery, designed to pull and shred material. Yet this existed long before humans imagined such tools. Another animal, discovered much later in Carboniferous deposits of North America, was so unusual that scientists initially believed the fossils were fraudulent combinations of unrelated parts. Tully monstrum gregarium, known as the Tully monster. Its body resembled a soft fish-like form with lateral fins and a tail, but its head extended into a long, flexible proboscis ending in a claw-like pincer. At the end of this appendage sat a mouth, not at the body's front. Two eyes projected sideways on a rigid bar stretching across the top of the head like a hammer. The arrangement defied classification. It did not clearly fit vertebrates, mollusks, or arthropods. Its internal structures were faint and difficult to interpret. Some studies suggested it had a notochord, placing it among early vertebrates. Others disputed this, arguing the features were preservation artifacts. Regardless of exact lineage, its feeding strategy was clear. The extended grasping organ allowed capture of small animals at distance, pulling them inward. The lateral eyes provided wide field vision, detecting motion across large angles. The body suggests active swimming rather than passive drifting. Unlike Cambrian organisms, the Tully monster lived in a complex ecosystem filled with established predators and prey. Its strange shape was not experimental randomness, it was specialization taken to an extreme degree. In the Devonian period, another shark introduced a different kind of absurdity: Stethacanthus. At first glance, it looked like a modest shark about 2 meters long. Then the dorsal fin appeared. Instead of a triangular stabilizing fin, males possessed a large, flat structure shaped like an ironing board or anvil, projecting upward from the back. Its surface was covered in tiny, tooth-like denticles, the same material forming shark skin and teeth. The function puzzled paleontologists. The structure would increase drag and reduce swimming efficiency, making the animal slower. It clearly did not help hunting. Evidence suggests it was used in mating displays. Males likely positioned themselves beneath females, pressing the textured surface against them as part of courtship behavior. Evolution sometimes favors reproductive success over survival efficiency. The Stethacanthus dorsal platform represents sexual selection overpowering hydrodynamic logic. It was not designed to help the animal live longer. It was designed to help it reproduce once. These creatures illustrate a shift in evolutionary strangeness. Cambrian animals seemed unreal because anatomy lacked established rules. Later animals seem unreal because they obey rules but violate expectations within them. Helicoprion followed the logic of a jaw yet turned teeth into a rotating blade. Tullymonstrum followed bilateral symmetry yet rearranged sensory and feeding structures into unfamiliar positions. Stethacanthus remained a shark yet sacrificed practicality for mating advantage. By this stage in Earth's history, ecosystems had stabilized enough that competition drove specialization instead of invention. creatures no longer tried every possible body plan. Instead, they pushed specific features to extremes, and extremes often appear unnatural. As ecosystems grew more complex, survival no longer depended on merely existing within an environment. It depended on outperforming neighbors. Competition reshaped anatomy into increasingly precise tools. The result was not always elegance. Sometimes it produced designs so narrow in purpose that they appear almost unreasonable. Helicoprion's spiral saw was not the only example of teeth evolving into something beyond simple biting. Another prehistoric shark relative, Edestus, lived during the late Carboniferous period, roughly 300 million years ago. Unlike Helicoprion, its teeth did not curl into a circular blade. Instead, the teeth formed two opposing curved rows, extending outward from the upper and lower jaws like serrated shears. New teeth grew continuously, pushing older ones forward without shedding. Over time, the jaws became elongated, scissor structures permanently exposed outside the mouth. The animal could not close its jaws fully in a conventional bite. It likely attacked prey by slashing upward or sideways, slicing flesh rather than grasping. Every feeding action required precision. If misaligned, the teeth could not reset like modern sharks. The weapon defined the behavior. This reveals a recurring pattern in evolution. Structures that become too specialized dictate lifestyle. An animal does not simply possess an adaptation, it becomes dependent on it. Edestus could not easily switch prey types or feeding strategies. Its anatomy forced a narrow ecological role. In freshwater environments of the same general era, strange design choices emerged in armored fish as well. Dunkleosteus, though a powerful predator, already followed recognizable vertebrate structure, but some of its relatives pushed cranial armor to extremes. Certain placoderms developed head shields so large that body flexibility decreased. Protection improved while maneuverability suffered. For them, survival depended on intimidation and durability rather than speed. These examples demonstrate a shift from experimentation to trade-off. Early life explored possibilities. Later life optimized specific advantages even at cost. On land, the same principle appeared among amphibian-like predators inhabiting swamp ecosystems. Some developed elongated bodies and flattened skulls, shaped almost like boomerangs. The genus Diplocaulus possessed a wide head extending sideways into long horn. For years, scientists debated whether these horns served defense, display, or feeding. Fluid dynamic modeling suggests the shape created hydrodynamic lift, allowing the animal to remain stable in flowing water. When currents pressed against the head, the horns prevented rolling and kept the body aligned. A skull became a stabilizing wing. The animal's entire survival strategy depended on maintaining position in shallow moving streams while ambushing prey. The design appears bizarre only because it merges two unrelated concepts: a head functioning as a control surface, yet Within its environment, it solved a specific physical problem more effectively than a conventional skull. Similarly, some ancient cephalopods evolved shells, not merely as protection, but as buoyancy regulators extending several meters in length. Their bodies occupied only a small chamber at one end, while the rest remained gas-filled. The creature effectively lived attached to a floating tower of chambers drifting vertically through the water column. Such forms illustrate that evolutionary pressure does not produce aesthetic balance, it produces adequacy under constraints. When one adaptation becomes successful, it may expand beyond what seems reasonable until environmental change renders it obsolete. The Tully monster exemplifies this phenomenon in classification rather than mechanics. Its uncertain placement among animal groups highlights how specialization can obscure ancestry. By altering enough structures, a lineage can lose obvious resemblance to its relatives. Over time, recognition disappears, even if descent remains direct. Extinction often follows excessive specialization. When conditions shift, a creature built for a single strategy cannot adapt quickly. Generalists survive change. Specialists dominate stability but vanish with disruption. This pattern explains why so many nightmare-like animals existed temporarily. They were not mistakes. They were solutions perfectly tuned to environments that no longer exist. Helicoprion depended on abundant, soft-bodied prey. When those populations declined, its unique jaw lost advantage. Edestus required particular hunting motions unsuited to new competitors. Diplocaulus relied on shallow waterways that later ecosystems replaced. Nature does not preserve the most impressive design, it preserves the most flexible. To modern observers, these animals appear unreal because they violate expectations shaped by surviving species. We assume efficient designs persist, but persistence depends more on adaptability than effectiveness. The prehistoric world was filled with creatures that functioned brilliantly within narrow windows of time. Their bodies were logical responses to precise conditions, yet outside those conditions they would fail immediately. Evolution does not aim for permanence. It aims for momentary success, repeated long enough to reproduce. The nightmares of the fossil record were often masterpieces of short-term engineering. Size is one of the most powerful forces in biology. Every increase in scale changes how muscles function, how lungs gather oxygen, how blood moves through vessels, and how skeletons resist gravity. Modern animals exist within limits set by atmospheric composition and structural efficiency. Elephants, whales, and the largest dinosaurs approached these limits, but rarely exceeded them for long. Yet in earlier ages, Earth allowed creatures to grow beyond what seems possible today. The difference was not magic. It was chemistry. During the late Carboniferous period, roughly 320 million years ago, atmospheric oxygen levels were dramatically higher than modern levels. Today, the air contains about 21% oxygen. At times during the Carboniferous, it may have reached 30 to 35%. This altered physics itself for living organisms. Oxygen diffuses into tissues more easily at higher concentrations, especially in animals that rely on passive respiration systems rather than lungs. Insects do not breathe using lungs. They absorb oxygen directly through small openings called spiracles that lead into branching tubes called tracheae. This system works efficiently only over short distances. As an insect grows larger, oxygen struggles to reach internal tissues. Modern insects are therefore limited in size. But in a high oxygen atmosphere, diffusion penetrates deeper. Larger bodies become possible without suffocation. This is why the skies once held dragonflies with wingspans wider than a hawk, Meganeura. With wings stretching nearly 70 centimeters across, Meganeura was not merely a scaled-up dragonfly. Its entire ecology differed. It could glide long distances with minimal effort, conserving energy while patrolling swamp forests. Small amphibians and other insects likely served as prey. Unlike modern dragonflies that rely on rapid flapping, Meganeura could remain airborne using sustained lift due to its size and wing surface. The air itself supported giants. On the forest floor, something far larger crawled through leaf litter and fallen trunks. Arthropleura. Often compared to a millipede, Arthropleura reached lengths exceeding 2 meters and widths approaching half a meter. Its segmented exoskeleton formed overlapping plates, allowing flexibility while maintaining protection. It possessed numerous legs that distributed weight efficiently across soft ground, preventing sinking into swamp sediments. Despite its intimidating appearance, evidence suggests it was herbivorous. It likely fed on decaying plant matter, ferns, and primitive vegetation. No known bite marks or predatory adaptations appear in its fossils. It was a gentle giant in a world where plants had not yet evolved modern defenses such as tough wood or chemical toxins. Its size protected it from predators rather than aiding attack. Few creatures could challenge it. Early amphibians existed but lacked jaws capable of penetrating its armor. Arthropleura occupied a niche similar to large grazing mammals today, processing plant material and recycling nutrients across the ecosystem. The presence of such enormous arthropods reshaped the environment. Their movement created pathways through vegetation. Their feeding accelerated decomposition. Their molting shells contributed nutrients to soil chemistry. Scale affects not only the individual, but the landscape. Yet, the age of giants extended beyond insects and land arthropods. In the oceans, millions of years later, a different lineage achieved enormous size through an entirely different mechanism. Reptiles had begun dominating marine environments following the decline of earlier amphibian predators. Among them appeared a snake relative that surpassed all modern serpents, Titanoboa. Living around 60 million years ago in warm, tropical wetlands of what is now South America, Titanoboa grew over 13 meters long and weighed more than a small car. Unlike Carboniferous giants enabled by oxygen, Titanoboa depended on temperature. Reptiles are ectothermic. Their metabolism relies on external heat. In warmer climates, they can sustain larger body mass because internal processes function efficiently without excessive energy expenditure. Paleoclimate analysis indicates average temperatures during Titanoboa's time exceeded modern tropical conditions significantly. The environment acted as a natural incubator, supporting enormous cold-blooded predators. Titanoboa hunted much like modern boas, using constriction rather than venom. It likely targeted large fish and early crocodilians along riverbanks. Its body mass allowed it to overpower prey with minimal struggle. Water supported much of its weight, enabling movement that would be impossible on dry land for a snake of such size. The existence of Titanoboa demonstrates that size limits are not fixed. They depend on environmental parameters. Lower global temperatures today prevent snakes from reaching similar scale because metabolism could not sustain activity. The giant disappeared not because it was inefficient, but because conditions changed. Large size also affects behavior. A predator of that mass requires less frequent feeding. It can dominate territory through presence alone. Smaller animals alter their habits, avoiding certain waterways entirely. Thus, the ecosystem reorganizes around a single organism's capabilities. Across eras and unrelated groups, one pattern repeats. When environmental constraints loosen, life expands physically. Arthropleura, Meganeura, and Titanoboa did not evolve toward gigantism as a goal. They simply encountered conditions where larger forms worked better than smaller ones. But when those conditions tightened again, the giants vanished. Nature allows excess temporarily. Permanence favors moderation. Gigantism is not only a result of favorable conditions. Once achieved, it changes how an organism interacts with the world so profoundly that it becomes a survival strategy in itself. Large animals do not merely compete differently. They exist under different rules of risk, energy, and time. A small predator must hunt constantly. A large predator hunts rarely but decisively. A small herbivore hides. A large herbivore endures. The balance of fear shifts with scale. During the late Paleozoic and early Mesozoic eras, some ecosystems contained very few organisms capable of challenging the largest inhabitants. Without strong predation pressure, natural selection no longer forced compact, efficient bodies. Instead, it allowed expansion. Arthropleura benefited from this. Its size was not only possible due to oxygen levels, but advantageous because it removed nearly all threats. Young individuals may have been vulnerable, but adults likely had no consistent predators. Growth therefore directly increased survival probability. Evolution favored individuals that matured larger and lived longer, reinforcing the trend across generations. Yet, size has costs. Movement becomes slower. Reproduction takes longer. energy requirements increase even if feeding frequency decreases. A giant survives easily during stability but struggles during disruption. Environmental change strikes large species first because they require more consistent resources. The Carboniferous forests eventually declined as climates shifted and oxygen levels fell. Swamps dried and plant communities changed. The conditions supporting giant arthropods disappeared gradually. Smaller insects adapted. Large ones could not shrink quickly enough through evolution. Arthropleura vanished without needing a sudden catastrophe. The same principle applied to aerial giants. Meganeura relied on atmospheric density and oxygen concentration to sustain flight. As oxygen decreased, wings that once produced lift became insufficient. Smaller dragonflies replaced them, maintaining the same ecological role at reduced scale. The niche persisted, while the giant form did not. In water, the relationship between size and environment becomes even more complex because buoyancy offsets gravity. This allows aquatic organisms to reach extraordinary masses without skeletal collapse. However, oxygen availability still matters. Large marine animals require efficient circulation or high dissolved oxygen content. During warm Paleocene climates, tropical wetlands supported immense reptilian life, including Titanoboa. But as global temperatures cooled over millions of years, metabolic limitations emerged. A snake of that size could no longer maintain digestion rates or movement speed necessary for hunting. Smaller snakes inherited the lineage better suited to fluctuating conditions. Gigantism also influences evolutionary pathways indirectly. When a species becomes dominant due to size, it alters selection pressures on other organisms. Prey species evolve caution, speed, or camouflage rather than armor. Smaller predators shift diet to avoid confrontation. The giant reshapes the food web not through constant interaction, but through presence alone. Consider the river systems Titanoboa inhabited. Large crocodilian relatives likely avoided waters where it hunted frequently. Fish populations concentrated in regions beyond its reach. Birds nesting near shorelines adapted to detect disturbances early. Entire communities organized around avoidance patterns. This effect resembles ecological gravity. The larger the organism, the wider the behavioral orbit of other species around it. However, the influence disappears quickly after extinction. Unlike gradual adaptation, gigantism leaves few successors. A giant's niche is often too specific to inherit directly. Instead, ecosystems redistribute roles among multiple smaller species. After Titanoboa vanished, no single reptile replaced its dominance. Crocodilians diversified. Mammalian predators later entered waterways. Control became shared rather than centralized. The fossil record shows that extreme size rarely persists continuously across geological time. It appears in bursts when environmental parameters align, then retreats. Dinosaurs achieved massive sizes under stable, warm climates and abundant vegetation. Yet, after environmental upheaval, only smaller descendants survived. Gigantism therefore represents opportunity rather than destiny. When physics allows, evolution explores it. When constraints return, life compresses again. To modern observers, creatures like Meganeura or Arthropleura seem unreal because they contradict everyday experience. We instinctively understand weight and structural limits through the present environment. Yet those limits are temporary conditions, not universal rules. Earth has repeatedly shifted the boundaries of what bodies can sustain. Each time, life expanded to meet the new maximum, then contracted when the boundary narrowed. The giant did the oceans. Life no longer appeared experimental or fragile. It appeared deliberate. Bodies were streamlined, skeletons reinforced, and senses sharpened for pursuit. Yet some predators became so specialized and powerful that they feel less like animals and more like machines designed for a single purpose. Among the earliest of these formidable hunters was a creature that did not rely on teeth in the usual sense: Dunkleosteus. Living during the late Devonian period, about 360 million years ago, Dunkleosteus was a placoderm, a group of armored fish whose heads and thoraxes were encased in thick bony plates. Many placoderms were modest in size, but Dunkleosteus grew up to 10 meters long and functioned as an apex predator of its seas. Instead of teeth, it possessed sharpened bony plates, forming self-sharpening blades along its jaws. When the mouth closed, these plates slid past one another, maintaining a cutting edge without replacement. Biomechanical studies estimate its bite force exceeded that of many later marine predators, capable of crushing bone and armor alike. Its jaws opened with astonishing speed. Muscles attached to hinged skull plates allowed rapid expansion of the mouth cavity, creating suction that pulled prey inward before the bite even occurred. The action combined vacuum force and slicing pressure. Once trapped, escape was unlikely. Unlike sharks that rely on multiple teeth and repeated bites, Dunkleosteus often required only one decisive strike. Fossil evidence shows healed bite marks on other Dunkleosteus individuals, suggesting aggressive encounters and even cannibalism. In its environment, survival meant constant readiness for confrontation. The seas it inhabited were filled with armored fish, early sharks, and numerous smaller species. Armor had evolved as protection against predation, yet Dunkleosteus rendered such defense temporary. Its cutting plates could shear through protective shells that once provided safety. This triggered a familiar evolutionary response. Some prey species became faster rather than stronger. Others shrank in size to avoid detection. The arms race escalated. Hundreds of millions of years later, reptiles entered marine ecosystems and refined the concept of the apex predator even further. Sarcosuchus. Often called the super crocodile Sarcosuchus, lived during the early Cretaceous period and reached lengths exceeding 12 meters. Unlike modern crocodiles that ambush prey from water edges, Sarcosuchus inhabited massive river systems capable of supporting its enormous mass. Its skull alone approached 2 meters in length. Its teeth were conical and interlocking, ideal for gripping rather than slicing. The jaw pressure was immense, but its strategy depended less on crushing and more on holding. Large dinosaurs approaching water to drink risked sudden capture. Once seized, drowning completed the attack. Growth rings in fossilized bones indicate Sarcosuchus continued growing for decades, reaching sizes few predators could challenge. It dominated freshwater environments, much as large marine reptiles ruled the oceans. But in open seas, another hunter appeared whose anatomy perfected aquatic pursuit, Mosasaurus. Living near the end of the Cretaceous period, Mosasaurus was a marine reptile descended from land-dwelling lizards. It possessed a streamlined body, powerful tail fluke, and paddle-like limbs. Unlike earlier marine reptiles, it could swim with sustained speed rather than brief bursts. Its jaws contained multiple rows of teeth, including secondary teeth on the roof of the mouth. This prevented prey from escaping once captured. Fish, ammonites, seabirds, and even other marine reptiles fell within its diet. Evidence suggests it could swallow large prey whole or tear pieces through shaking motions, similar to modern crocodilians. What distinguishes Mosasaurus is its adaptability. It hunted in deep water, near shorelines, and across varied conditions. While Dunkleosteus relied on brute force and Sarcosuchus on ambush, Mosasaurus combined pursuit, maneuverability, and grip. It resembled a fusion of snake flexibility and whale power. Predators like these alter ecosystems profoundly. Their presence limits the distribution of other large animals. Prey evolve schooling behavior, faster swimming, or protective shells. Smaller predators shift to different feeding niches. Yet, their dominance also makes them vulnerable. Apex predators depend on abundant prey and stable environments. When disruptions occur, they lack fallback strategies. Their specialization becomes fragility. Dunkleosteus vanished during Devonian extinction events that reshaped marine life. Sarcosuchus disappeared as continental climates and river systems changed. Mosasaurus perished during the catastrophic end, Cretaceous extinction that eliminated non-avian dinosaurs. Each ruled completely during its time. Each left no direct equivalent afterward. They were not simply large animals, they were peak expressions of predatory design under specific conditions. And once those conditions vanished, so did they. Apex predators influence ecosystems in ways that extend far beyond the individuals they consume. Their true power lies not only in killing, but in shaping behavior. When a hunter becomes dominant enough, other animals begin organizing their lives around avoiding it. Feeding times change, migration routes shift, and even reproduction patterns adapt to minimize encounters. In the Devonian seas ruled by Dunkleosteus, Armored fish did not simply to isolate a target. The rise of collective movement in aquatic life may have been driven as much by fear as by efficiency. This behavioral evolution spreads through generations. Individuals that respond quickly to approaching shadows survive. Those that hesitate vanish. Over time, entire species carry inherited caution. A predator, therefore, alters prey not only physically, but psychologically, embedding awareness into instinct. Sarcosuchus produced similar effects in freshwater environments. Massive riverbanks that appeared calm could conceal a hunter capable of lunging upward with explosive force. Large herbivorous dinosaurs approaching water would likely pause, scan, and approach cautiously. Fossil trackways near ancient shorelines sometimes show sudden direction changes or retreat patterns consistent with alarm behavior. This constant tension shapes landscapes. Areas near water become less densely traveled. Vegetation grows differently where grazing decreases. Smaller animals occupy spaces avoided by larger ones. The predator indirectly engineers the environment. In marine ecosystems, Mosasaurus exerted influence over enormous distances. Its ability to patrol both deep and shallow waters removed safe zones for many creatures. Schools of fish clustered tightly for protection. Ammonites evolved thicker shells and complex sutures to resist crushing. Even other marine reptiles adapted by developing faster swimming styles or shifting feeding depth. Such pressures produce innovation but also instability. When one predator dominates too completely, ecosystems become dependent on its presence. Remove the predator suddenly, and prey populations surge uncontrollably, disrupting balance in the opposite direction. Extinction events reveal this effect clearly. After the Devonian extinction removed large placoderms, including Dunkleosteus, shark diversity expanded dramatically. Without competition from armored giants, new predatory forms filled vacant niches. The system reorganized rapidly, not gradually. At the end of the Cretaceous period, the disappearance of Mosasaurus and other marine reptiles allowed surviving fish lineages and early sharks to diversify. Marine food webs simplified temporarily before stabilizing again under new rulers. Fear vanished, then reappeared in different forms. This cycle illustrates an important pattern. Apex predators rarely persist continuously through geological time. Instead, different groups repeatedly rise to occupy the same ecological role. Placoderms, large sharks, marine reptiles, and later marine mammals, each controlled oceans in succession. The position remains constant while the occupant changes. Why do apex predators tend toward extreme forms? Because partial dominance fails. A predator competing with equals must conserve energy and avoid injury. A predator far above competition can afford risk. Over generations, natural selection favors increasing power until efficiency gives way to intimidation. The hunter becomes overbuilt for ordinary encounters, but optimized for absolute control. Dunkleosteus jaws could crush armor thicker than most prey possessed. Sarcosuchus could seize animals larger than necessary for survival. Mosasaurus could attack nearly anything within reach. Each exceeded the requirements of daily feeding because dominance itself prevented challenge. However, exceeding requirements increases vulnerability to environmental shifts. When prey numbers fall or climates change, the same specialization that once secured dominance prevents adaptation. Smaller generalist predators survive by switching diet. Giants cannot. Thus, extinction follows success. The most perfectly adapted hunters often vanish first when conditions deteriorate. Their reigns are intense but brief compared to more modest species. To modern observers, these predators appear monstrous because they represent evolutionary peaks rather than averages. Most animals exist near balance points between energy cost and gain. Apex predators sit beyond balance, occupying extremes possible only under stable conditions. They are less like ordinary creatures, and more like moments when nature pushed a single role to its maximum expression. When most people imagine prehistoric mammals, they picture small nocturnal creatures hiding beneath the feet of dinosaurs. For much of the Mesozoic era, that image is accurate. Early mammals survived through caution rather than dominance. They were compact, warm-blooded, and adaptable, waiting for opportunities rather than shaping ecosystems. But after the extinction that ended the age of dinosaurs, mammals inherited an open world. Forests, plains, and river valleys contained empty ecological roles once occupied by reptiles. Evolution responded rapidly. Within a few million years, mammals diversified into forms so unusual they often seem unrelated to modern species. One of the strangest was a predator whose appearance challenges expectations of mammalian anatomy, Andrewsarchus. Discovered from a massive skull found in Mongolia, Andrewsarchus lived around 45 million years ago during the Eocene epoch. The skull alone measured nearly 1 meter long, larger than that of a modern grizzly bear. Yet, its structure did not resemble a cat, dog, or bear. The snout was elongated and narrow, while the teeth combined slicing carnivore blades with crushing molars. For decades, scientists debated its body shape because only the skull was known. Earlier reconstructions depicted a gigantic wolf-like hunter. Later research suggested closer relation to early hoofed mammals, possibly resembling a massive predatory pig with long legs built for running along coastlines and floodplains. The teeth reveal a flexible diet. Andrewsarchus likely hunted animals, but also scavenged carcasses and crushed bone or shellfish. Its jaw mechanics allowed both shearing flesh and grinding harder material. Instead of specializing, it dominated through versatility combined with size. Its existence demonstrates how early mammals explored ecological roles without established competition. Carnivorous mammals today belong to a defined group, Carnivora, with similar skeletal patterns. Andrewsarchus lived before that group fully diversified. mammals were still experimenting with how a large predator should be built. Another creature from South America took mammalian experimentation in an entirely different direction. Macrauchenia. At first glance, it resembled a camel without a hump, but its nostrils sat high on the skull near the eyes rather than at the snout tip. This suggests the presence of a short trunk, similar to a tapir. Its long neck allowed browsing vegetation above ground level, while 3 toed feet supported running across open plains. Macrauchenia belonged to a lineage isolated in South America for millions of years. Without competition from horses or camels initially, mammals evolved into parallel forms that filled similar ecological niches yet followed different anatomical paths. Convergent evolution produced familiar functions using unfamiliar structures. When Charles Darwin encountered its fossils during his voyage, he recognized both similarity and difference compared to modern animals. It resembled multiple species, yet matched none exactly. The mammalian body plan proved flexible enough to recreate roles independently across continents. Perhaps the most unsettling mammal of this era was not a predator but a herbivore, Chalicotherium. It possessed the body proportions of a horse, but ended in long curved claws instead of hooves. Its forelimbs were longer than its hind limbs, giving it a sloped back. Rather than running across grasslands, it likely stood on hind legs and pulled branches downward using claws, feeding like a browsing giant sloth. The claws were not weapons, but tools for gathering food. Walking required bending the wrists inward to avoid damaging them, producing a knuckle-walking gait similar to modern gorillas. A creature built like a hoofed runner, instead moved like a climbing primate. This mixture of traits reflects mammals adapting to vegetation before grasses dominated landscapes. Forest environments favored reaching and grasping rather than speed. Later, climatic changes replaced forests with open plains, favoring hoofed runners. Chalicotherium declined as its feeding strategy became inefficient. Early mammalian evolution did not follow a direct path toward modern forms. It spread outward in many directions, testing combinations of features inherited from small ancestral insect eaters. Large size arrived quickly once competition from reptiles disappeared, but structure varied widely. Andrewsarchus explored predatory dominance through power and flexibility. Macrauchenia recreated browsing herbivores using independent ancestry. Chalicotherium modified locomotion to interact physically with vegetation. These animals appear unrealistic because modern mammals represent only surviving branches. Earlier diversity included body plans, later eliminated by environmental change and competition. What seems abnormal now was once common possibility. After the extinction of the non-avian dinosaurs, mammals did not simply grow larger versions of their former selves, they spread into nearly every ecological position available. Some became swift runners across open plains, others climbed trees, and many returned to the water. But during this expansion, evolution had not yet settled on the streamlined forms familiar today. The result was a temporary age in which mammals often looked assembled rather than refined. Andrewsarchus demonstrated how a predator could arise from hoofed ancestry, yet in other regions entirely different mammals became dominant hunters. South America, isolated for millions of years, produced its own large carnivores, unrelated to wolves or cats. These animals evolved slicing teeth and forward-facing eyes, similar to modern predators, but their skeletal structure revealed herbivore origins. The distinction between grazer and hunter blurred during this period because mammalian lineages were still flexible. This flexibility explains why early ecosystems contained creatures performing identical functions with completely different body plan. Modern ecosystems appear orderly because long competition filtered forms into a few efficient templates. Early Cenozoic environments had not yet undergone that long filtering process. Macrauchenia represents another outcome of isolation. In the absence of camels or horses, mammals evolved to fill browsing roles independently. Its long neck allowed feeding above ground vegetation, while its trunk likely grasped leaves and possibly detected scent. The elevated nostrils may have aided breathing while partially submerged, suggesting it inhabited wetlands and floodplains. Such adaptations show that mammalian features were rearranged rather than invented. The same bones present in early ancestors were lengthened, shortened, or repositioned. Evolution rarely creates entirely new structures. It modifies existing ones into unfamiliar proportions. Chalicotherium illustrates this principle most dramatically. Hoofed mammals typically depend on speed for survival, yet this animal sacrificed running ability for feeding efficiency in forested environments. Its claws enabled pulling branches toward its mouth, reducing the need to move constantly between feeding sites. Energy conservation replaced mobility as its main strategy. Fossilized wear patterns on its teeth indicate a diet of soft leaves rather than abrasive grasses. When global climates cooled and forests retreated, grasslands expanded. Grasses contain silica particles that wear teeth quickly. Grazing mammals evolved high-crowned teeth to withstand constant grinding. Chalicotherium lacked such adaptations. Its feeding specialization became disadvantageous. The disappearance of these mammals was not due to weakness, but to environmental shift. As habitats changed, selection favored animals capable of traveling long distances in search of scattered food. Hooves, once reduced or modified, regained importance. Speed again became survival. Early mammals therefore demonstrate a repeated evolutionary cycle. Opportunity leads to diversification. Diversification leads to specialization. Specialization leads to vulnerability when conditions alter. This pattern also affected sensory systems. Some mammals developed elongated snouts for smell, others enlarged eye sockets for vision, and some strengthened hearing structures. Because competition remained low initially, extreme variations could persist without immediate elimination. Over time, predators and prey refined each other's abilities, until only efficient combinations remained. Modern mammalian diversity appears wide, yet it is only a remnant of this earlier exploration. Many intermediate forms vanished because later competition compressed ecological roles into narrower categories. Predatory mammals converged towards similar limb posture and dentition. Grazers evolved comparable digestive systems. The unusual hybrids disappeared. To observers today, a hoofed predator or a clawed horse seems contradictory because modern groups are distinct. But during the early age of mammals, those distinctions had not solidified. Classification lines we consider natural are historical outcomes rather than inherent divisions. The unreal appearance of these animals reflects the temporary freedom evolution experienced after the extinction of dominant reptiles. For a brief geological moment, mammals tried nearly every possible arrangement of limbs, teeth, and posture. Eventually, ecosystems stabilized again. Familiar body plans prevailed because they balanced efficiency with adaptability. The strange mammals did not fail. They were early drafts of roles, later rewritten in cleaner form. What survives in the present is not the full story of mammalian potential, only the versions that remained practical as Earth continued to change. On land, size is limited by gravity and support. In the ocean, buoyancy changes everything. Water carries weight, allowing bodies to expand without collapsing under their own mass. As a result, some of the strangest and largest predators in Earth's history developed not on continents, but in open seas where physical constraints were relaxed. Yet freedom from gravity did not produce familiar giants. Instead, it produced animals whose proportions seem exaggerated beyond reason. One of the earliest was a cephalopod, unlike any living squid or octopus, Camaraceras. Living roughly 470 million years ago during the Ordovician period, Camaraceras resembled a massive, straight-shelled nautiloid. Its conical shell could reach lengths approaching 9 meters, far larger than most other animals of its time. The living body occupied only the front chamber, while the remaining shell contained gas-filled compartments used for buoyancy control. From the opening extended numerous tentacles surrounding a sharp beak capable of grasping prey. Rather than chasing victims with speed, Camaraceras likely drifted vertically through the water column. By adjusting internal gas pressure, it could rise or sink silently. Small fish and other organisms swimming nearby would suddenly encounter a descending forest of tentacles. Its shell acted both as flotation device and defensive armor. Few predators could damage it. However, the shell also limited maneuverability. Camaraceras did not pursue prey over long distances. It functioned as a slow-moving trap in open water, capturing organisms through position rather than pursuit. This method represents a different concept of predation. Instead of speed and force, it relied on patience and scale. In a time when fast swimmers were rare, simply occupying a large volume of water increased feeding success. Hundreds of millions of years later, Another marine giant appeared, though built on entirely different principles, Edestus. During the Jurassic period, this enormous fish reached lengths over 15 meters, rivaling modern whales in size. Unlike most large predators, it fed by filtering plankton from water using specialized gill structures. Its mouth opened wide to allow continuous flow while swimming slowly through nutrient-rich seas. Its skeleton was lightly built compared to its length, reducing energy costs. Instead of hunting individual prey, it harvested entire microscopic populations. The strategy resembles modern baleen whales, yet evolved independently long before mammals returned to the oceans. Fossil remains show frequent injuries from large marine reptiles, suggesting predators attempted attacks but rarely succeeded against full-grown individuals. Its sheer mass served as protection. A hunter would expend enormous energy for uncertain reward. The existence of Edestus demonstrates that gigantism does not require predation. Abundant microscopic life can support massive bodies when feeding systems scale efficiently. Oceans provide continuous food distribution, unlike land environments, allowing filter feeders to grow far larger than terrestrial herbivores. Meanwhile, sharks continued evolving unusual feeding mechanisms. The spiral-toothed Helicoprion from earlier periods represents only one variation. Some relatives developed crushing plates instead of sharp teeth, consuming shelled animals. Others evolved elongated jaws extending outward during feeding. In marine ecosystems, diversity of prey encourages diversity of mouths. Hard shells, soft bodies, schooling fish, and floating organisms each demand different solutions. Because water supports body mass, extreme cranial structures become viable without compromising movement. The ocean therefore preserves anatomical oddities longer than land. Terrestrial animals must balance locomotion with feeding apparatus. Marine animals can exaggerate feeding structures dramatically while maintaining buoyancy. Camaraceras use size and vertical ambush. Edestus use filtration and continuous motion. Sharks use specialized dentition. All represent different answers to the same question: how to gather energy efficiently in an environment without solid boundaries. To a human observer, these animals appear unreal because they challenge assumptions formed on land. We expect predators to chase and herbivores to graze. In open water, strategies expand beyond those categories. When the end Cretaceous extinction occurred, highly specialized animals disappeared disproportionately. Generalists with flexible diets and behaviors survived more readily. The strange dinosaurs were not inferior. They were precisely tuned to environments that no longer existed. Classification challenges arise because scientists reconstruct relationships using surviving evidence. Bones reveal structure, but rarely behavior fully. Without modern analogues, interpretation requires inference. Early reconstructions often exaggerate familiar traits to fit expectations. Only additional fossils gradually clarify true form. For example, Therizinosaurus claws were once imagined as predatory weapons because claws in modern reptiles serve that role. Later discoveries of body posture and teeth changed interpretation toward feeding adaptation. Similarly, Dinosaurus arms initially suggested aggression until stomach contents indicated otherwise. This process shows that perception of realism depends heavily on comparison. Animals, unlike anything alive today, appear implausible even when mechanically sound. Yet, each had functional anatomy consistent with physics and ecology. Evolution does not produce creatures to match human intuition. It modifies existing organisms step by step according to immediate advantage. Over long periods, this can lead to combinations that look contradictory because their ancestral functions differ from their final use. The fossil record preserves these moments of transition. They reveal that familiar biological categories are temporary arrangements shaped by survival, not permanent divisions embedded in nature. The unreal appearance of such creatures reflects the narrowness of modern experience. If they had survived into the present, they would seem ordinary, and different extinct animals would instead appear impossible. Long before dinosaurs, before fish, and even before the Cambrian creatures that already seem strange, Earth hosted organisms so unfamiliar that scientists struggled to decide whether they were animals at all. These beings lived during the Ediacaran period over 550 million years ago, a time when complex life existed but had not yet adopted recognizable anatomy. There were no eyes, no mouths, and no limbs. Movement, if it occurred, left only faint traces. Many organisms absorbed nutrients directly through their surfaces rather than consuming prey. Their bodies resembled patterns more than creatures. One of the most studied examples is Dickinsonia. Its fossil appears as an oval imprint divided into repeating rib-like segments extending from a central axis. The segments are not symmetrical like modern arthropods. Instead, they follow a glide reflection pattern, where each unit mirrors the previous one with slight offset. This geometry is rare in modern animals, but common in mathematical tiling. For decades, scientists debated whether Dickinsonia was an animal, a giant protist, a fungus, or even a colony of microbes. Chemical analysis of preserved molecules eventually detected cholesterol derivatives associated with animal metabolism, strongly suggesting it belonged within the animal kingdom. Yet its feeding standard, the body functioned as a continuous surface interacting directly with the environment. There was no clear front or back, only a direction of slow progression. Nearby lived other organisms resembling quilted cushions, fronds, or branching leaves. Some stood upright, anchored to the seafloor, absorbing nutrients from water currents. Others lay flat, maximizing surface area for diffusion. Without predators requiring defense, shape depended on water support and simple internal organization. They demonstrate that complex size preceded complex organs. When the Cambrian period began, many of these forms vanished rapidly. The emergence of active predators and burrowing animals disrupted microbial mats and introduced new pressures. Creatures unable to defend themselves or move effectively declined. However, the Ediacaran organisms are not evolutionary failures. They represent a separate experiment in complexity. Instead of developing mouths and mobility first, they expanded surface interaction with the environment. Later, animals internalized processing through digestive tracts, allowing faster energy intake and active behavior. The difference resembles passive absorption versus active consumption. Both sustain life, but one scales poorly once competition appears. To modern observers, Dickinsonia seems unreal because it lacks defining animal features, yet it satisfies biological criteria: growth, metabolism, and reproduction. Its body plan demonstrates that early multicellular life explored pathways later abandoned. Studying these organisms alters understanding of evolution. Complexity did not progress smoothly toward familiar animals. Multiple forms of organization coexisted, and only some persisted. The ones that led to modern ecosystems represent a subset, not a predetermined goal. The earliest complex life looked less like creatures and more like living textures across the sea floor. They were alive without appearing animated. The Ediacaran world was quiet, not silent in sound, because water still moved and sediments shifted, but quiet in action. There were no chases, no sudden attacks, no jaws snapping shut. Life existed without urgency. Energy entered bodies slowly, and bodies responded slowly. Time functioned differently for organisms that did not yet compete through speed. Dickinsonia and its relatives occupied vast microbial plains where sunlight supported mats of bacteria and algae. These mats formed stable food layers across the seafloor. Because no animals yet burrowed deeply into sediment, the surface remained intact for long periods. Entire communities depended on this stability. Each organism absorbed nutrients directly from contact with the mat or surrounding water. Some resembled leaf-shaped fronds anchored upright, maximizing exposure to gentle currents. Others lay flat like patterned carpets, expanding outward as they grew. Growth often followed geometric repetition rather than centralized organs. Segments repeated because repeating structures are simple to build genetically and function adequately without complex coordination. Reproduction likely occurred by releasing cells or fragments into water, allowing new individuals to settle nearby. Without predators reducing population, density could increase until resources thinned, after which growth slowed naturally. The ecosystem regulated itself through nutrient availability rather than behavioral interaction. Then conditions changed. As oxygen levels rose and genetic innovations accumulated, some organisms developed the ability to move with purpose. Even minimal movement created advantage. A creature able to reposition toward thicker microbial patches gathered more energy than one waiting passively. Over generations, structures supporting directed motion improved. The first mouths formed as depressions, concentrating nutrient intake. Instead of absorbing across an entire surface, energy could be gathered faster through a single opening. Faster intake allowed more active tissues such as muscles and nerves. Active tissues enabled escape and pursuit. The quiet world became dynamic. This transformation did not gradually modify Ediacaran organisms into Cambrian animals. Evidence suggests many Ediacaran forms disappeared rather than adapting. Their body organization lacked the internal differentiation needed for rapid change. They were successful under stability but inflexible under disturbance. Burrowing animals disrupted microbial mats, removing the continuous food layer Dickinsonia depended on. Predators consumed soft-bodied organisms lacking defense. Water chemistry altered as sediments mixed. The foundation of the previous ecosystem collapsed. Yet the importance of these organisms lies not in survival, but in demonstration. They show that animal-like complexity emerged before familiar anatomy. Multicellular coordination, large body size, and ecological communities existed without eyes, limbs, or digestive tracts. Modern animals inherited only one branch of early possibilities. We recognize that branch as normal because it persisted. The Ediacaran branch appears alien because it ended. If environmental conditions had remained stable longer, surface-absorbing organisms might have diversified further, perhaps developing different complexities unrelated to later animals. Instead, mobility and ingestion proved more adaptable under changing circumstances. The fossil record preserves this transition as a boundary between two styles of life. Below it lie impressions of quilted forms resting on undisturbed sediment. Above it appear tracks, burrows, shells, and bite marks recording interaction and conflict. The unreal creatures of the Ediacaran period represent a world where life existed without struggle in the modern sense. They remind us that the competitive ecosystems familiar today are not inevitable outcomes, but consequences of particular evolutionary choices. Earth once supported living beings that resembled patterns more than animals, organisms that fed without eating and lived without fleeing. Their disappearance allowed the rise of active life, but their existence reveals how different biology could have been. The history of life is often told as a march toward familiarity. Simple organisms become complex, water becomes land, reptiles become mammals, and eventually the modern world appears inevitable. But the fossil record does not describe inevitability. It describes selection. At every stage, more forms existed than survived. The Cambrian seas held animals that looked assembled from unrelated parts. Later, oceans contained predators built like cutting tools. Swamps supported insects the size of birds, and rivers hid snakes longer than buses. Mammals once walked on claws where hooves now run, and dinosaurs experimented with wings that vanished before flight was perfected. Even before animals truly existed, patterned organisms covered the seafloor, like living geometry. None of these were mistakes. Each functioned within its environment. Each was a working solution to the conditions of its time. Extinction removes not only species, but entire possibilities. When Hallucigenia's relatives declined, a style of armored, soft-bodied walking life faded. When placoderms disappeared, bone-bladed jaws vanished with them. When giant arthropods shrank, the atmosphere itself became less permissive to such scale. When specialized dinosaurs died, their unusual experiments in feeding and movement ended abruptly. The Ediacaran organisms represent perhaps the greatest loss. A complete alternative design for complex life erased before it could diversify further. The present world, therefore, is not the best of all forms. It is the remaining set. Every modern animal carries limitations shaped by past filters. Mammals breathe through lungs because that path survived. Birds fly with feathers because membrane wings in their lineage did not continue. Fish use fins because earlier propulsion strategies failed under competition. The familiar body plans surrounding us feel natural only because alternatives are gone. If a different extinction sequence had occurred, the world might appear equally coherent, yet entirely foreign. Oceans could be dominated by drifting tentacled shells rather than fast swimmers. Land could host clawed herbivores instead of hoofed grazers. Large surface-absorbing organisms might share environments with mobile predators. Even intelligence could have arisen from a lineage unlike mammals or birds. Evolution does not predict outcomes. It filters variations through circumstance. The strange creatures of the past remind us that biology is not guided toward a final form. It constantly explores, but most explorations end. The survivors define normality, and memory defines strangeness. What appears unreal is simply what no longer continues. Fossils preserve these lost directions. They show moments when life tried different arrangements of sense, motion, and feeding. Some were inefficient, others highly effective, yet fragile to change. Success depended less on perfection than on compatibility with shifting environments. This perspective alters how we see modern ecosystems. Present species are not permanent achievements, but temporary occupants of roles repeatedly filled by unrelated groups across time. Apex predators rise and fall. Giants expand and contract. Specialized forms flourish briefly, then disappear when conditions move beyond their tolerance. Humanity occupies one of these temporary roles. Our technology and awareness do not place us outside evolutionary processes. We persist under current conditions and may vanish under others. The fossil record suggests that even dominant organisms are transient. Yet there is continuity beneath change. The genetic and chemical foundations of life connect all these creatures across hundreds of millions of years. The same molecular systems powered Dickinsonia's absorption, Dunkleosteus's bite, and modern metabolism. Variation occurs in structure and behavior, but the underlying chemistry remains shared. This continuity makes the past less alien than it appears. The unreal creatures were not separate creations. They were relatives expressing possibilities later pruned. The distance between them and us is measured in time and survival, not in belonging. Studying them expands understanding beyond what exists now. It reveals that life's potential is broader than current examples suggest. Many viable forms have come and gone without leaving descendants. Their disappearance narrows perception of what living systems can be. The fossil record is therefore not merely a catalogue of extinction, it is a record of imagination tested by reality. Nature produced far more designs than endured. Each layer of rock holds alternatives that once competed with ancestors of modern species. To see them as curiosities misses their significance. They represent paths evolution could follow again under new conditions. Different climates, atmospheres, or ecological structures might favor forms that resemble ancient ones or combine traits in unfamiliar ways. The boundaries of the possible remain wider than the present indicates. The unreal creatures are reminders that life does not converge on a single answer. It searches continuously, and the world at any moment shows only the latest results of that search. Imagine observing Earth from far beyond time rather than space. Not a single moment, but the entire history unfolding at once. The continents shift like slow currents, oceans open and close. Ice advances and retreats. Against this changing stage, life does not move in a straight line. It pulses. Diversity rises rapidly, stabilizes briefly, and collapses. Each collapse does not end life, it reorganizes it. The world after each extinction is not emptier for long, it becomes unfamiliar. Before the Cambrian period, large, patterned organisms rested across the seafloor in quiet abundance. Afterward, mobile animals filled the same ground with tracks and burrows. Later, armored fish ruled the seas until replaced by sharks, then marine reptiles, then mammals. Forests once dominated by towering ferns gave way to conifers, then flowering plants, then grasses. Each transformation replaced entire communities rather than modifying them gently. The creatures in this script belong to these pulses. They represent peaks that defined their time completely, yet left little visible continuation. Consider the difference between disappearance and replacement. When Dunkleosteus vanished, oceans did not lack predators. New hunters evolved with different anatomy, but similar ecological function. When giant insects declined, smaller ones inherited the same airspace. When unusual mammals faded, more efficient grazers and carnivores occupied their niches. Function persists while form changes. This reveals a deeper pattern in evolution. Roles endure longer than bodies. A filter feeder will exist as long as plankton thrives, but it may be a fish, a reptile, or a mammal, depending on era. A large river ambush predator may be an armored fish, a reptile, or a mammal. Even gliding through forest canopies appears repeatedly across unrelated lineages. The environment demands certain solutions. Evolution repeatedly invents them using available materials. Therefore, the strange creatures are not isolated anomalies. They are previous answers to ongoing questions. Each extinction resets the design process, allowing new structures to attempt the same tasks. From this perspective, the modern world is simply the latest arrangement, not a final one. Future fossils will show our present ecosystems as transitional. Species that seem permanent today will appear as temporary experiments tomorrow. What determines survival across these cycles is not strength, intelligence, or size alone. It is adaptability to change speed. Organisms specialized for narrow conditions flourish during stability but vanish quickly during disruption. Generalists persist but rarely dominate for long. The balance between efficiency and flexibility decides duration. Many animals discussed earlier were highly efficient. Helicoprion processed prey with precision. Arthropleura thrived under high oxygen. Therizinosaurus exploited specific vegetation. Their disappearance reflects environmental shift rather than biological flaw. Their designs matched their time perfectly. The lesson extends beyond biology. Stability creates complexity, but complexity increases fragility. The more precisely a system fits its environment, the more sensitive it becomes to alteration. Life repeatedly builds elaborate structures that later conditions dismantle. Yet this cycle does not imply meaninglessness. Each rise adds possibilities. Later organisms inherit genetic and ecological groundwork laid by earlier ones. Mammals diversified rapidly after dinosaurs, not only because dinosaurs vanished, but because previous ecosystems had accumulated nutrients, soils, and atmospheric composition, enabling new growth. Extinction clears space, but also depends on what existed before. The unreal creatures therefore contribute to the present indirectly. They shaped the pathways that allowed later survivors to exist. Even failure leaves structure for the future. Seen across deep time, the history of life resembles a conversation rather than a progression. Each era proposes forms, the environment responds, and the next era answers differently. No single statement concludes it. We recognize only the current reply because we live inside it. Fossils preserve earlier replies, reminding us that the familiar once did not exist and will not always remain.